The dominant perspective among researchers is that existing models about the origin of the cosmos continue to serve as the fundamental explanation for how the universe began. This foundational theory outlines how stars and planetary systems came into being, a progression that eventually brought forth life forms, including human beings. Although the name may seem strange, the Big Bang concept presents a rich narrative describing the potential events that marked the universe's earliest moments. Initially, all matter and energy in the universe were concentrated in an incredibly minuscule point, significantly tinier than the head of a pin, where particles were tightly compressed. From this ultradense origin, an enormous outburst of matter and energy, commonly referred to as the Big Bang, occurred. This colossal eruption, which happened billions of years ago, initiated the ever-expanding journey of the cosmos. Yet, as humanity's grasp of astrophysics and cosmology expands, cracks in the traditional Big Bang framework are starting to surface, bringing forth new challenges to long-standing assumptions. With the deployment of the James Webb Space Telescope, JWST, an observatory hailed as the most advanced and sizable space-based instrument ever devised, astronomers anticipated that it would solidify support for the Big Bang theory. But astonishingly, within merely a year of operation, the telescope's phenomenal capacity to observe the distant reaches of the universe revealed discoveries that stunned the scientific establishment. The telescope's extraordinary vision has unearthed galaxies from an era so ancient, it throws into question previously accepted ideas about the universe's origin. This development has ignited intense debates over whether material might have existed prior to what we currently define as the Big Bang. One of the most pivotal milestones came when cosmologist Rohan Natu, combing through data collected by the JWST, identified a galaxy formed not long after the Big Bang itself. This galaxy is now considered the most remote and oldest ever detected. The implications of this find rippled through the scientific community, showcasing just how transformative the JWST's technology truly is. The telescope's capacity to revolutionize our cosmic comprehension is just beginning to unfold, bringing forth promising new clues about the universe's primordial epoch. This time span, loosely interlinked with pre-existing cosmological ideas, holds the essential clues to how the earliest clusters of stars and galaxies came into being. The insights brought forth by the JWST are already clashing with traditional models, revealing galaxies that possess properties scientists previously thought implausible at such early stages. This sudden boom in early universe galaxies has sparked a surge of excitement and deep questioning among experts, prompting an urgent reevaluation of current frameworks. As researchers delve deeper into this new data, they are being confronted with profound inquiries concerning the very fabric of the cosmos and the elemental forces that dictated its early development. Apart from its revolutionary findings, the JWST's physical positioning provides it with critical advantages. It operates at a location approximately 1.5 million kilometers away from our planet, shielded from terrestrial interference and maintained at frigid temperatures near absolute zero thanks to a massive sunshield comparable in size to a tennis court. Its large gold-coated primary mirror and highly sensitive instruments were engineered specifically to peer into corners of the universe that have remained obscured, until now. The period this telescope is unveiling, often dubbed the Cosmic Dawn, took place about 200 to 300 million years following the Big Bang. This was the epoch during which the first luminous bodies, stars and galaxies, began to flicker into existence. However, the mechanisms behind these events remain hotly debated, with many hypotheses revolving around the roles of dark energy, invisible dark matter, and the interaction of star-forming gases and interstellar dust. The JWST's unique ability to detect galaxies from this crucial juncture provides cosmologists with a rare opportunity to rigorously test or reshape their theoretical models. By dissecting data from these distant systems, they can either verify the robustness of their frameworks or unearth inconsistencies that may lead to paradigm-shifting revelations. At the beginning of its mission, expectations for the JWST were conservative. Scientists believed it would detect only a modest number of faint, early universe galaxies. But these expectations were swiftly eclipsed. The telescope's debut snapshots of the ancient cosmos unveiled a staggering array of galaxies differing in age, size, and brightness, numbers and characteristics that vastly exceeded what had been anticipated. This torrent of early galactic data has prompted an intense scientific race. to redefine what qualifies as the earliest colossal system in the universe. Findings continue to pour in, surprising even the most seasoned astronomers. As the JWST's observations accumulate, both the scientific world and the general public have been captivated by the complexity and advancement of these newfound galaxies. While some scientists hypothesize that potential misinterpretations of the telescope's large-scale observational techniques could account for some anomalies, the majority consensus leans toward viewing these discoveries as a groundbreaking reorientation in our understanding of cosmic history. These insights offer an exciting window into a universe that might be far more intricate and puzzling than prior models had imagined. The emerging evidence surrounding these ancient galaxies, made possible by the JWST, poses serious questions about our foundational beliefs concerning the universe. While some researchers are optimistic that these anomalies can be incorporated into existing cosmological theories, others argue that they might signify the first clues pointing to a far more mysterious and layered universe than we ever considered. The overarching question continues to linger. How did the orderly cosmos we recognize today rise out of the chaotic, primordial crucible that marked its beginning? The telescope's early revelations might dramatically reshape not only the prevailing view of the Big Bang but also offer fresh interpretations of remote galactic structures, some of which may even alter our grasp of our own galaxy, the Milky Way. As Mark McFadden, a senior science leader at the European Space Agency, aptly summarized, the purpose of creating instruments like the JWST isn't merely to confirm established theories, it's to challenge and potentially dismantle them. You never truly know what might be overturned, he emphasized. The concept of the JWST can be traced back to 1985, well before the Hubble Space Telescope took flight. At the time, Garth Weir, then director of the Space Telescope Science Institute, STSCI, was charged with envisioning what might follow in Hubble's footsteps. Though many were skeptical at the outset, Weir and a dedicated team laid the initial foundation for what would eventually evolve into the James Webb Space Telescope. Where Hubble specialized in capturing images in visible wavelengths, the JWST was specifically engineered to operate in the infrared spectrum. This choice is vital because light from faraway galaxies, due to the expansion of the universe, is redshifted into the infrared range, rendering it invisible to optical telescopes like Hubble. The JWST's enormous, ice-cold mirror enables it to detect these elusive signals, allowing astronomers to peel back cosmic layers to a time closer to the universe's origin than ever before. The critical necessity for such a telescope became undeniably clear in 1995 when Hubble's deep-field imagery revealed countless galaxies in a seemingly vacant patch of sky. This eye-opening revelation demonstrated just how populous the early universe truly was and underscored the urgent need for a telescope with even greater reach. After decades of meticulous planning, development, and a financial investment totaling around $1 billion, the JWST was finally launched on December 25, 2021. By July 2022, it was fully operational and ready to begin its pivotal scientific mission. Research initiatives like the Early Release Science (ERS) program and the General Observing Program were established to hunt for the universe's earliest galaxies. Initial predictions were cautious, but the telescope's first wave of data quickly surpassed them. JWST observations have already begun to test, and in some cases topple long-standing models of the universe's infancy. These findings serve as a powerful reminder of why stretching the limits of exploration and investing in cutting-edge technological tools are so essential. With each new batch of data streaming in from the telescope, researchers find themselves on the verge of potentially rewriting everything we thought we knew about the cosmos. When the first transmissions from the JWST were released, the anticipation was electric. Scientists who had been preparing analytical tools and models for years were finally able to put them to use. Rather than adhering to the slow-moving, traditional peer review system, many researchers chose to publish their findings immediately via preprint platforms like AR14, enabling rapid access and instant critique. This method sparked widespread and swift discussion, especially on social media platforms such as Twitter, where experts could weigh in almost in real time. Cosmologist Rohan Natu described this approach as science by press release, a nod to the speed and visibility of the scientific dialogue that ensued. While this openness facilitated accelerated feedback, Some scientists express concern that it might jeopardize the thoroughness of conventional scientific scrutiny. Klaus Pontoppidan, a lead project scientist for the JWST at STSCI, cautioned that although this high-speed sharing of discoveries allowed for rapid collaboration and insight exchange, it also threatened to overwhelm the careful structure that typically defines the scientific process. The deluge of major discoveries from such a high-stakes project presented new hurdles for traditional workflows, but the consensus among researchers remains that these challenges are a worthwhile price for the immense knowledge being gained. As it stands, the Big Bang model is still broadly recognized as the cornerstone explanation for the formation of our universe, including the origin of stars, planetary systems, and life itself. Though its name might be misleading, the Big Bang theory lays out a coherent, science-backed narrative about how everything came into existence. At its start, the universe existed as a compact, incomprehensibly dense singularity, smaller than a grain of sand, where particles were crammed together tightly. From this nearly dimensionless point, a tremendous eruption of energy and matter occurred, catalyzing the expansive evolution of the cosmos we now observe. But as the JWST continues to gaze deeper into the void of time, its discoveries are beginning to expose the limits and gaps within the original theory. The revelations of galaxies forming in an era far too early to align with current timelines suggest that the story of our universe is far from complete. These findings not only challenge the framework of the Big Bang but also open new pathways for understanding the underlying principles that shape everything, from the smallest atomic particles to the largest galactic clusters.